3, 2, 1.
Okay, so this vacation, I've been taking this machine learning course from Coursera, and it's all about, if you have a set of data points, these crosses here are data points, and some x-axis and y-axis, and you want the machine to learn how to predict values based on this training set. These crosses here are a training set. So, okay, the simplest case, you create a straight line through the crosses and use the straight line to predict new values in the future. The line equation is y equals kx plus m. Maybe you have different letters, but this is the base equation. M is the intercept term. It's where the line crosses the y-axis. And k is the slope of the line. But instead of that, you can use theta 0 and theta 1. Theta 0 is the intercept term here, and theta 1 is the k term. And here, theta 0 and theta 1, you can put it into a vector, and that fits very good into MATLAB or Octave. Okay. So here we can load some example data. Here we have some example data, 97 rows and 2 columns. Let's look at it. So I don't really know what it is. It's x values here and y values here. So let's look at it. Do a scatter plot. Let's just pick out first ex1 data of the first column and set y to the second column and plot. Not so good. Let's do a scatter plot instead. Here we have it, and the line, we want to fit a line here. So the intercept term should be somewhere around here. And then the slope, I don't know. We move 5 units in the x direction and move how much? Maybe 5 units in the y direction. Maybe around 1. Slope around 1. Right. So let's do this. In Octave, we have the cost function defines, what is this? This is the error between the line and the crosses. So in the y direction, take the difference between the cross and the line, sum it up, and take the square of it, and divide by the number of crosses. And one cross here is one sample. So divide by the number of samples. But really, because of technical details, you divide by 2 times the number of samples. And it's called the cost function. And to know when you change theta 0 and theta 1, this is the intercept term, this is the slope. To know how the error will change, you have to take the derivative. And the derivative is like here's the cost function. The line here is called a hypothesis minus the real values for the crosses here. All right, square them, sum them up, divide by 2m. And this cost function, if you vary theta 0, which is the intercept term, and theta 1, which is the slope, and compare with the slope, you will see that it will become a 3D surface, and you want to find the minimum here. Here's the error is smallest possible. This is the best fit for the line, okay? So the values for theta 0, theta 1 here. This is what we want. So our goal is to minimize this function, theta 0, theta 1, and j. And to do that we need derivative, and here is the formula for the derivative of the cost function. All right, it's a lot of math, and if you haven't done calculus, it's probably gibberish. But you just put this into MATLAB. All right. Let's see, the cost function. What does it take? An x and y. Come on. 97 m's, okay. And x ones, m ones in one column, and the current x. That's it, okay. Then we have a column of ones and a column with the actual x values. All right, and the y values is here. Okay, what do we need? X, y, and theta is the guess. It's the guess for the intercept term and the slope. So let's just call cost with x, y, and a vector. Let's just guess 0, 0. So the cost is 32 here. Let's guess -1 for the intercept term and the slope 1. -1 for the intercept and slope 1. Okay, so the cost is much lower. So that was a better guess. And to automate this, we put it into an algorithm that's called gradient descent. That's actually, you take the cost function, derivative of the cost function, and change the guess. And the step size, it's called alpha here. It's on a parameter. It's telling how big steps to take each iteration. And after a number of iterations, this will, you know, hopefully get smaller and smaller and smaller until it goes towards the minimum value. All right, let's try it. Two outputs. Theta is the values for intercept and slope, a vector of two values, and j is the, for each iteration, it's an array of costs, or a vector of costs, which you can plot and see if it looks okay. All right, let's call it, let's say theta and j equals gradient descent x, y, initial guess for theta, let's set that to 0, 0. And alpha, let's set to small alpha, 0, 0, 1. And let's set it to like 1,000 iterations. And it finds theta -3 and the slope 1.1, okay? I wonder how good is it. Let's do the scatter again. Scatterplot. And then let's do a line plot here. Hold this. No, hold on. Of what? Let's set x to what? From 5 to 25. Go from 5 to 25. All right, and set and plot. And the equation is -3.2414 plus 1.173 times x. All right, so here are the dots, and here is our guess that minimizes the error. So it looks like a pretty good fit. So that is like the basis of machine learning. It's guessing a straight line through a number of dots. And when you have this straight line, you have a model or a hypothesis. And these dots are called a training set. And when you got a straight line, then you have your model, and then you can use this straight line to predict new values. Let's say a new customer comes along and have, let's say this is a house sizes area. They have an area of 15 units, whatever units they use. So you can predict the prices around 13, whatever units the prices. So that looks like a good estimate. There's a little bit of variance, so okay, it's 15, you can expect maybe it can vary from here to here, but the mean guess should be around here. And then you can, of course, if you have dots that go like this, then you maybe use another hypothesis, not a straight line. A straight line is called a linear regression. Maybe you use another function instead to try to fit a line, square root, or x squared. Use more degrees, x cubed, and you need to add combinations of x squared, x squared, and x cubed, and all possible combinations, and you get a lot of parameters. But then you can get a good curve that fits the points very well. But you don't want to fit them too well, because then it will be overfit. It will try too hard to fit the training set, and then it will not predict very well new values. It should be a pretty good fit, but not too good fit. That's the ground rule. All right, and that's it for me in this video. It's the very first beginnings of the machine learning class on Coursera, and then it goes on and on and on with neural networks and support vectors machine and so on.